platform, so bear with me if I have some problems with sharing the screen, etc. But I will try. So let's see how this works. Do you see my screen now?
Yes.
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 Perfect. Okay.
Yes,
So
yes.
yeah, I will make the full screen mode soon. But before I start, so thank you first all this for this opportunity, Daniela, for giving this series of lectures. It's a great pleasure for me to be in contact with people in Naples and Campania in general. So it is I regret that I cannot be there in person, of course. So it would be much nicer for all of us, especially for me. But let's make the most of it. So first of all, I will start by showing you a cover of the book that just came out in last December. So this is a book that we wrote together with Daniela Calvetti, and this is based on a series of experiments with this topic with our students. So we started some 12 years ago, maybe, to collect the material, and when we started to teach a course which was first called data mining, and then we decided to call it data science because that seems to be the word that people are using now. What this course is about, it is a basic introduction to certain topics in data science, mostly clustering and classification. So those are the two topics which are pretty central in modern data science. This course is not covering the very popular area of neural networks, which is kind of a little bit of different topic. It would be certainly useful to look at that too. There are some ideas, basic ideas in this course, which are lying, behind the ideas of neural networks. But so this is not about neural networks. So this book does not contain projects or exercises, but we know how valuable they are both for students and for people who are teaching this course. So we have a Google site which is under Daniela Calvetti's website. So you see the address here at the sorry. On the bottom of this page. And so let me show you what this website looks like so that you have a little bit of an idea. So this is the website, and so what we have here on the website, we are trying to collect projects and data sets that you can use to test these ideas. So they are organized according to the topics that we are covering. So there is a series of questions on principal components. There is about k-means and k-medoids, linear discriminant analysis, self-organizing maps, non-negative matrix factorization, text mining, tree regression, and there will be more. So while we are moving with our course here, we are teaching this course currently, and so we are collecting these projects here so if you just go to the web page, you will have access to all that material. And there are also data sets that you can download. So far, we have been using MATLAB, but as if you read this book, there is in the introduction also mentioned that there will be also Python material available. We haven't just had time to organize the material so that we would have the Python support there, but this page is under construction, and you will have more material there in the future. So and so if you have questions, just stop me and I try to answer. I try to follow the chat also, but I am not always paying attention to that. So I'm happy to answer questions and clarify if something is not clear. So let me see now. I want to go to full screen, right? Here we go. Okay, so So what is data science? Let's start with the basics. So traditionally, when we are talking about science, science is studying nature broadly construed. So nature is not only the nature, flowers and animals, but yeah, or physics, but also like economy and psychology and nature broadly construed. And so, what is the traditional approach in quantitative research in science is to try to build models, and using those models, you try to infer on nature. So you are trying to extract information on nature, and the current understanding is then encoded in mathematical models. So we are trying to put in the models all that we know about our target or object of interest. And this model or those models need to be then validated. And so there's where data comes in. So you can think of the work of Newton. So he had his work on gravity, and so then he was validating with experimental data. So data was a vehicle from nature to theory. And parameter estimation is one of the big things in this validation process. And so that's one thing that inverse problems are addressing. So you have the data and you try to understand which parameters in your model are explaining the data. Now in data mining, the object of interest is no longer so much nature, but it's data itself. So you can think that the data takes the place of nature. So we have these data sets, and basically we don't care what they are representing necessarily. Of course, it helps us to know something about the data, but so you can think that you have texture images and you don't really care what the texture image is about. So it could be some sand samples, or it could be let's say fractures in a metal structure or so. So you have this data, and you are not trying to model the data by talking about what is it representing, but you are looking at the data itself. So you're trying to find a structure in the data itself. So the data becomes the nature in this case. And the underlying models are often in data science of less importance. So we are not really trying to see the structure in data by using the models that we have, but we are just trying to see what the data itself is telling us. And so if you think of classical statistics, data-driven statistics, you see that there is a strong connection. And actually, some people say that statistics is the original data science, and that may be a good characterization of statistics. Statistics, however, has its own language, and if you want to do statistical analysis, you have to immerse yourself into that language. Data science has developed its own language. This is not necessarily the same as in statistics. And in this course, the goal is try to follow the other language, let's say, not the statistical terminology. So what we are doing here is we are looking at data not as a statistical object. We are not talking about probability densities and etc. We are just looking at basically as a collection of vectors. So that's the typical picture here. So we have some order structure like this set X, which consists of vectors x1, x2, x, etc. xn. Typically n is large, so that's what makes data science so special. You have usually lots of data. And those vectors X have components. Those components are often referred to as attributes. So you have different attributes that you have collected in your vectors. And those attributes need not to be reals, although they often are. So we are trying to use quantitative methods, and quantitative methods are heavily using the ideas from linear algebra, for instance, where you prefer having the attributes to be real numbers, but it may be something different. So here is a fictitious example. We have x1, x3, and x2 and x3. So the first attribute is a real. The second attribute is like a fruit, banana, apple, pineapple, and the third attribute is a logical true-false attribute. So this is a possible structure of your data. So, but often we assume, as I said, that these XLs are vectors in Rn. We are discussing what should be done if this is not the case. So we need to have some quantitative methods, and sometimes you have to do a conversion of your data into something that you can treat using mathematical tools. Now, often n, which is the number of attributes, is much less than the number of data points. So n is here the number of attributes, like 3 here, and n is the number of vectors you have. And so there are examples where this is not the case. So take genetic data. So typically genetic data is like genome data. So you have a huge dimensional space, and you may have several hundred only observations. So now your data space is enormous, and the samples relative to the number of attributes is small. But so most of the time we are assuming that we have much more realizations of the data than we have the attributes. So that's a general situation here. Okay, so as I mentioned, these lectures are based on linear algebraic methods. Not only linear algebra, but linear algebra is a useful tool. And so therefore the first lecture today is a summary of linear algebra, not so much because I think that you are not familiar with linear algebra, but to fix the notations and definitions, so that when I'm later referring to what I mean by my linear algebraic tools, you can go back and check what notations I was using. So in our book, there is the first chapter, which is a linear algebra primer. I'm not going through all of it because I'm not using all of it, at least at the beginning. So if we need to go back to the linear algebra, I will complete this part. But so we start with some linear algebra. And as I mentioned also, this course is not using tools from statistics. So we are using more linear algebraic language than statistical language. So we are not talking about correlations, similarities of vectors. We are looking at, for instance, inner products. So you know that two vectors are similar if the inner product is large, because the same components at the same time are large. So that's the way we are looking at similarity of vectors. We are not talking about regression in this course. We are talking about solutions to linear systems. So linear regression is basically another way of saying that you are solving a let's say least squares problem, for instance. So we are looking at solutions to linear systems rather than regression. Although there is a clear connection, as I mentioned. We are not talking about marginalizations in the sense of probability densities. We are projecting data. So we are ignoring some of the components by projecting the data vectors to lower dimensional subspaces, and you can say that this is similar to marginalization in statistics. We are not talking about variances of the data. We are talking about spread, so how wide the data set is, etc. So there's a clear connection with statistics, but this course is not mixing with the terms of statistics. So this is strictly staying on the, let's say, non-statistical language, which is leaning on linear algebra. And so, without further ado, I'm going to start introducing the notations and the basic definition, so that you know what we are talking about. So first of all, I'm going to use the notion of a vector in Rn, referring to a column vector. So typically, when I say a vector, you can think of a column vector, and the attributes x1, etc., xn are real numbers, and or components, of course, in the classical language of linear algebra. But so data science often refers to them as attributes. Now, two vectors can always be summed if they have the same number of components, and the summing is the usual component-wise summing. So you are adding the respective components, you get a new vector. And multiplication of a vector by a scalar is done by multiplying each component by that scalar. And so this structure makes a vector space. So the vectors are vector space is a collection of vectors that make sure that you are not falling out of the space by summing and multiplying vectors by scalars. The other important object besides vector is of course a matrix, of which a vector can be thought of as a special case. So matrices are n times p arrays of real numbers, so that the first component, the index is referring to the row, and the second index is referring to the column. And so we are denoting this that R is in Rn times p. N is the number of rows and p is the number of columns. And again, like vectors, we can add and multiply matrices by scalars. So multiplication of a matrix by a scalar means that you multiply all components by the same scalar, and summing two matrices of the same size. Notice they have to be of the same size, n by p. So then what you do to add those matrices, you just add component by component. So this is the this formula here is defining the multiplication by scalar and the summation of matrices of the same dimension. So nothing surprising here. Now, transpose means, of course, that we are changing the role of the rows and columns. So you start with the matrix A, which is here. You take the first column and you make it a row in your transpose. So you make it a row. You take the second column and you make a row of it. And so this way you get the transpose of the matrix. And if your original matrix was n by p, the transpose is p by n. So you're reversing the role of rows and columns. And of course, transpose of the transpose give you back the matrix. And so the matrix vector product is an important object, and often it is defined component by component. So if I have a vector x which has components xl, I have a matrix which has components akl. So what you do, you take a row at a time from your matrix, and then you multiply with the column component by component, then you're summing up. So this is the formal definition of the matrix vector product. It is a vector whose kth component is akl times xl, and then summation over L from 1 to p. And so now you see that this is possible only if the number of components in your vector x is the same as the number of columns in your matrix A. So that's the only case in which you can form the matrix vector product. Well, this is the component-wise definition. Since we are talking about data, the fundamental objects that we are looking at are columns of a vector. So a matrix. So when we take a set of data, we typically organize the data so that the data vectors are columns of a matrix. And so therefore, it is useful to think matrix vector products in a different way. And so here is a different interpretation. So you can say that A of x is a vector which is a linear combination of the columns of the matrix A. So you take a linear combination of the columns, and the multipliers are x1, x2, etc., xp. So that is the components of x. So A of x is a special linear combination of columns of A. And so that's a useful way of looking at matrix vector products. We can also define a matrix product provided that those matrices have compatible sizes. So let's take a matrix B whose columns are B1, etc., Bm. So these lines here are indicating that we are talking about column vectors, B1, etc., Bm. They are column vectors of length p. So if I have a matrix A which is of size n times p, then I can multiply with this I can multiply each column of my B vector by the vector A, because we know how the matrix vector product is working. And so you get a new matrix whose columns are now matrix vector products. And notice these are every column here in this product AB is again a linear combination of the columns of A. And we can write this in component-wise fashion. So AB is a matrix whose ijth component is the sum of the products A, I, L, B, L, J. And the summation runs over the L index, which is the sort of the inner index. So if you take these A components and B components, the components which are close to each other, they have to be the same, and then you are summing over those components. So standard definition. So nothing new. Now we are defining the inner product or the dot product. I'm calling it inner product of two vectors of the same size. So take x and y. Now take a transpose of x, and so if your x was a column vector, the next transpose is a row vector. And then you have the y vector. They have the same amount of same number of components by definition because they're in Rn. And so then you multiply component by component these vectors, and then you sum up. And so out comes a scalar. And so this is the inner product. And so in particular, if you take x equals y, so the next transpose x is simply the square sum of its components of x. And so this is larger or equal to 0, and you see also that it is 0 if and only if all components of x are 0. And so then the important concept, which is a geometric concept, and it is sort of a generalization of what you observe just by looking at vectors in R3 or R2, is we say that two vectors are perpendicular if their inner product is 0. So this is the important orthogonality property. Perpendicular orthogonal. So I'm using the word orthogonal. So, but the idea is that the vectors are perpendicular if you are in a physical 3 space or 2 space. So two vectors are orthogonal if and only if the inner product is 0. That's an important property. Further, we are defining vector norms. So vector norm is any assignment mapping vectors to non-negative scalars and denoted by these two bars if that assignment satisfies 3 fundamental properties. First of all, the norm has to be positive definite. That means that the norm of any vector has to be larger or equal to 0, and it should be 0 if and only if x is a 0 vector. That is, all the components are 0. That's number one. The second one is positive homogeneity. So if you're multiplying your x by a scalar alpha, so this absolute value of alpha can be pulled out from the norm. And the third one is triangle inequality. It says that x plus y is a vector whose norm is less or equal to the norm of x plus the norm of y. If those 3 properties are satisfied, then we have a norm. And so that norm can be any assignment that satisfies those 3 fundamental properties. And since we already encountered this inner product of x with itself, so if you take a square root of x transpose x, you get the normal Euclidean vector norm, which is the square root of the square sum of the components of x. So this is the normal Euclidean distance. And if no indication of which norm we are talking about in the case of vectors are given, so then I mean this Euclidean vector norm usually. I hope I'm not changing idea, you know. But so the idea is that normally we don't if we know what norm we are talking about, so we just use the notion of the norm and denote it without any decoration. But this 2 here is reminding that this is the Euclidean vector norm. And why 2? Because you can define other vector norms. So here is the p norm. So you take, instead of the square sum, you take the sum of the pth powers of the components, and then you take 1 over p. So that 1 over p guarantees that your norm is going to be positive homogeneous. And so you see that if p is 2, then we have the Euclidean norm. Now sometimes we are using p equals 1, which is the 1 norm, which is a very useful norm, and we will also use that in this course, data science. And then the infinity norm is simply the maximum of the absolute values of the components of xj. And so if you wonder why it's called infinity norm, it is because if you take this p norm and let your p go to infinity, then in the limit you get this maximum. Oh, by the way, this p here should be larger or equal to 1. So if you let p to be less than 1, then you won't have a norm. You have something which is a norm-like, but it is no longer convex. So the triangle inequality won't hold. So p has to be larger or equal to 1. Okay, so these are basically the norms that we are going to encounter in this course. One norm, infinity norm, and Euclidean norm for vectors. For matrices, we need to define different norms. And so there are two views of matrices that decide which norm concept we are using. So you can think matrices as arrays of numbers. So you can say the matrix is what they are. So they are arrays of numbers. And so then you can measure the size of the matrix by looking at the sizes of the components simply. And so that's one view. And then there's another view. Remember, matrix is multiplying vectors. So you can think matrix as an operator. So it sends a vector to another vector. And so that's what vector is what the matrix is doing. So not what matrix is, but what it is doing. So and that brings another concept of norm, which I will define soon. But so let's look at first the idea of matrix as an array of numbers. So A is a collection of vectors which are arranged in the columns of A. So now you can measure the size of each column. So take, let's say, the 2 norm. So this is a 2 norm here. So you take the 2 norm of each column. So now you have a vector of norms. And then you take the 2 norm of those norms. And what you get is the Frobenius norm of A. And so the Frobenius norm, in other way of saying it, is the square sum of all components of A summed up over the row index and over the column index, and then square root of the whole thing. And so that's the Frobenius norm. So that tells you roughly how large the matrix is, in the sense that how large the components are. So this is a useful norm. Now, the other norm that I was mentioning, and the other view of matrices, is that you think matrices as operators. So they are sending vectors to vectors. So I take a vector x and I'm sending it to another vector a of x. And then I'm measuring the size of the outcome. And I'm comparing it with the size of the initial vector x. And so this ratio here tells me how much a is stretching or shrinking the vector x. So if this ratio here is larger than 1, then it means that a is stretching the vectors. If this is the vector x, and if this is smaller than 1, then it means that a is shrinking this vector. And so if I take maximum of all these numbers, so that gives me the maximum amount that the matrix can stretch a vector, and that's called the induced norm of A. And since this is based on the 2 norm, the Euclidean norm of the vectors, I'm denoting this matrix by 2. But you can use any norm here, so it doesn't have to be the Euclidean norm. You can use, let's say, the P norm if you like, and you can equally well define the induced norm. And so here is important calculation. So let's look at a of x. So this is the length of ax. Now I'm multiplying and dividing it by the length of x, assuming that x is non-zero. Of course, that's important. Now the ratio of ax divided by x is less or equal to the maximum amount of stretching that this matrix A can do. So I can estimate from above this ratio by taking the maximum. Well, by definition, this maximum is the induced norm of the matrix A. And so you see that A of x is always less or equal to the norm of A times the norm of x. So this is an important relation. And so it's easy to understand what this means if you remember what the induced norm is doing. So here is a picture of this situation. So I start with vectors which have been scaled so that they all have length 1. So these green, red, and blue vectors, they are vectors of length 1. So then I'm applying my matrix A on all of them. And so out comes 3 vectors here. And turns out that these vectors are, the tips of those vectors are on an ellipse. And so now you can go around this ellipse and you can try to find the vector who has the maximum length. And in this case, the red one is the maximum length here in the image side. And so the length of this red vector on the right divided by the length of this red vector on the left is the norm of A. So it tells you how much A is capable of stretching vector. So that's the induced norm. Okay, so those are basic tools. We need a little bit of subspaces, concept of subspaces, and in particular there are 2 subspaces related to matrices that are of importance: the range and null space. So the range of A is the subspace which is spanned by all columns of A. And so if you remember what span means, spanning subspace, it is the subspace of all possible linear combination of the vectors which are spanning the subspace. So if I take the columns of my matrix A, then the span by definition is the set of vectors which are linear combinations of those columns. And now we should remember what matrix vector product was. It was just a linear combination of the columns of A. So another way of saying this, that is the range of A is the set of all vectors y which can be represented as A of x, where x is some vector in Rp. Rp, yes, right, that's correct. Okay, so range is all values that the mapping AX can obtain or attain when x is any vector. So that's range of a matrix. Then the null space of a matrix is the set of vectors which are mapped to 0. So if you have a vector x which is going to 0 when you multiply by A, so then that vector is in the null space of A. And are there any vectors that are going to 0? Sure, if you take x to be the null vector or 0 vector, then AX is clearly 0. So the null space contains at least one component which is 0, but it may contain other vectors too. So that's important to notice. So null space may be quite large. And so the concept of linear independency will play a role in this lecture. So suppose you have k vectors v1, v2, etc. vk. They are of the same length. They are in Rn. Now we say that those vectors are linearly independent if the only way to write a linear combination of those vectors equal to 0 is that those components are, those coefficients gamma 1, gamma 2, gamma k are all 0. Another way of saying this linear independency is that you cannot represent any one of those vectors as a linear combination of the others. So that's what the linear independency means, that no vector of v1 to vk can be represented as a linear combination of the others. So they are independent of each other in that sense. And so now if you take a matrix A whose columns are linearly independent, then you see that the null space of A has to be 0. And why is that? Because, let's go back. So we had the null space to be the collection of vectors which are going to 0, which are mapped to 0. So A of x is a linear combination of the columns of A. If the columns of A are linearly independent, so then x has to be in a null vector. And so therefore, the null space of A it consists only of one single vector, which is the 0 vector. So another way of saying that vectors are linearly independent is that you arrange them as columns of a matrix, and if that matrix has 0 null space, so then the columns are linearly independent. So those are 2 equivalent statements. I mentioned subspaces, and so subspaces, we have been already talking about subspaces without explicit reference to it. So the null space and the range, they are both subspaces, and subspace is characterized by the fact that if you take two vectors x and y in the subspace and you scale them as you wish, then the linear combination of those scaled vectors is still in the subspace V. So subspace is closed, so to speak, under the operations of sum and multiplication by scalar. So you never fall out of the subspace by scaling your vectors or summing the vectors. So that's a vector space, subspace. And oh, so sorry, that's a vector space to begin with. And now, if you have a subset of a vector space, then if that subset itself is a vector space, then we are talking about a subspace. So you may have you can think of R3, which is a vector space, and then you take R2, where the third component of the vectors is 0, and that's a subspace. So it is a vector space which is embedded into a larger vector space. And if V is a vector space, and you can represent your V as a linear combination of vectors in a set S, we say that this S is a spanning set. Spanning set means that all vectors can be expressed as linear combinations of the entries in this set. And so, as I mentioned, we have encountered vector spaces which are subspaces of Rn, and one is this range of A, which is a subspace of Rn, and the null space, which is a subspace of Rp. So notice that these two vector spaces are in a different space. So Ra is a vector space in the n-dimensional space, and null space is a subspace in the p-dimensional space. So they are not subspaces of the same space. Okay, so there's lots of definitions here that I'm going through, and this is simply so if you need to go back and check what I was saying, you can find this material in this lecture. But so I think it's important to set the notation. So we're going to talk about dimension of a subspace, and the dimension of subspace is the maximum number of linearly independent vectors in Rn. In V, sorry, not Rn. So so if you have a subspace V and you can show that every vector in V can be represented as a linear combination of two linearly independent vectors, so then the dimension is 2. So maximum number of linearly independent vectors in V is by definition the dimension of the subspace. And once we are there, so we call basis of V any set of linear independent vectors that span the subspace. So if you have two vectors that completely characterize your subspace so that these two vectors are linearly independent and every vector can be represented as a linear combination of those two, then you know that these two vectors form a basis and the dimension of your subspace is 2. And if you do so-called change of basis, so you are deciding that the basis that you are using is not good for you, you want to change the basis. Once you know the dimension of your subspace, the number of basis vectors must always be the same. So if I change from 2 spanning vectors to another set of spanning vectors which are linearly independent, then I know that the new set has to contain 2 linearly independent vectors. So the dimension cannot change by changing the basis. Another way of saying. Now, often it's convenient if your spanning vectors are mutually orthogonal. And so then we say that we have an orthonormal basis. An orthonormal basis, what does it mean? You have k vectors v1, v2, etc., vk. And first of all, since we are talking about basis, so these vectors have to be a linearly independent set of vectors, so they have to be a basis. Remember, basis means that they are linearly independent and they are spanning the subspace. But moreover, these vectors are mutually orthogonal. So if I take the inner product of two vectors with different index, I get 0. So these vectors are mutually orthogonal. And when we are saying orthonormal basis, we assume that these vectors are normalized. so that the Euclidean norm of each one of those vectors is 1. So that means that the inner product of VL with itself is 1. So now you have normalized so that the length of each vector is 1. So if you have those two properties for a set of vectors, so then these vectors form an orthonormal basis of the spanning subspace that they are spanning, which is k-dimensional in this case. Now there is something which is referred to as 4 fundamental subspaces. This is not terribly important in this course, but since we are there, I mention it. We may need to use this at some point. So we have this matrix A, and so we have already associated 2 vector spaces to it, namely the range of A, which is a subspace of Rn, and the null space of it, which is in the subspace of Rp. So now what happens if I take the transpose of A? So my matrix A is n by p, and if I take the transpose of A, I get the matrix of p by n. So then, of course, I can define the range of A transpose, and now this range of A transpose is in Rp, and notice that's in the same space. It's a subspace in the same dimensional space as where the null space resides, Rp. Also, I can look at the null space of A transpose, and that is a subspace of Rn, which again is the space where the range of A is a subspace. So now I have 4 subspaces. And so it turns out, and I'm not going to well, first of all, I give a definition. So the rank of matrix A is the dimension of its range. So rank means if you give me a matrix A and you ask what the range is, and I have to explain it to you. So the rank of A is the dimension of the subspace that its columns are spanning. So it is also, or you can say it another way, it is the maximal number of independent column vectors, linearly independent column vectors of A. So those are equivalent ways of defining the rank of A. And another way of saying it is the dimension of the range of A. So you give me a matrix, and I'm checking how many linearly independent columns my matrix has, and that's the rank of A. So that's the definition of rank. Now, interestingly, it turns out, and these are basic results in linear algebra, which I'm not going to prove and discuss either, but I'm just saying it. So if I take the rank of A, which I denote by R here, turns out that the rank of A equals the rank of A transpose. So if I take 2 matrices A and A transpose, they always have the same rank. So that means that the number of independent columns and the number of independent rows of a matrix is always the same. That's a beautiful and deep result somehow. And furthermore, it turns out that the dimension of the null space of A is P minus R. And the dimension of the null space of A transpose is N minus R. So once you know the rank of a matrix, you know the dimensions of all of these 4 subspaces. You only need to know one number, namely the rank of A, which is the dimension of the range. And then you know the dimensions of all of these 4 subspaces. That's not all. What is more is that the null space of A is orthogonal to the range of A transpose. So remember, the null space of A and the range of A transpose, they are subspaces of the same space Rp. Okay? Turns out that if I take any vector from the null space of A and I take any vector from the range of A transpose, those 2 vectors are always orthogonal to each other. So this is a nice and deep result from linear algebra. And the same is true for the sort of the dual picture. So if I take a range of A and I take the null space of A transpose, those are 2 subspaces in Rn. And again, if I take a vector from one space and a vector from another space, those vectors are automatically orthogonal to each other. So This means that this Rp and Rn, they can be decomposed in orthogonal components in the following sense. And this is the notation. So we sometimes we write like this. We say that Rp is the direct sum of the null space of A and the range of A transpose, and Rn is the direct sum of the null space of A transpose plus the range of A. And what does this notation, this plus in the circle mean? It means that if I take any vector from Rp, so let's look at this first one, Rp. So I take any vector x from Rp. I can always decompose x in two components, u plus v, where the first component u is in the null space of A, and the second component is in the range of A transpose, and this decomposition is unique. So there is no other way of decomposing your matrix, your vector A. So every vector has a unique decomposition into a component which is in the null space of A, and what is left is in the range of A transpose. This is a strong and beautiful result from linear algebra, and we may have to make reference to this result later. It is not central in this course, but it is certainly a useful result. Now, what is certainly central in this course is projection. So this is something that needs to be well understood. So let's look at two vectors, A and X. I'm referring to this picture here. So I can always decompose my X, which is an arbitrary vector in Rn, in two pieces. So one is parallel to A. So if it's parallel to A, it's some scalar times A plus the remainder. And I can choose this scaling gamma in such a way that this x perp, which is the remainder, is perpendicular to A. So if you look at this picture tells you that this is obviously true. So I take a vector of x, and then I look the shadow of x on the direction of A. And so I'm measuring the perpendicular shadow of x in that direction. And so that gives me the gamma A part, and the length is adjusted so that this gamma adjusted the length of gamma A so that this shadow is such that what is left, this other vector here, is perpendicular to A. And so now I'm summing these two vectors, gamma A, which is along this direction of A, of course, and then the perpendicular part. So this decomposition always exists, and so this gamma A is called the projection of x to the direction of A. So what is gamma? Let's go here. So suppose you need to resolve for this gamma. So what you can do, you use the fact that this x perp is perpendicular to A. So if I take the inner product by A and x, so I write A transpose x. So A transpose x gives me gamma times A transpose A, and then the inner product with x perp, but that's 0. So here is the calculation. A transpose x is gamma A transpose A plus A transpose x perp. And so this second term here is 0 because my x perpendicular is assumed to be perpendicular to A or orthogonal to A. And so therefore the inner product by definition must be 0. So what I'm left with is gamma times A transpose A, which is the same as the Euclidean norm of A. And if this matrix, this vector A is non-zero, I can divide by the length of A squared and I get gamma. So gamma is A transpose divided by the length of A squared times x. So notice this is a scalar because it is A transpose x, which is a scalar, divided by another scalar, which is the length of A. I'm just writing it this way so that you see that it is an inner product with the scaled vector A transpose divided by A squared and x. And so now if I denote this gamma A as a matrix that is acting on x, so I want to find a matrix PA acting on my vector x so that the outcome is gamma A. So then if you look at this gamma A here. So here is gamma, and let's multiply it by A. So what I get is 1 over A squared is here, and then I have A transpose X, and then I have this A by which I multiply this gamma. And so I'm calling this PA of X. And so now you can identify the matrix that is mapping my X to this projection PA of X. The matrix is given here. So this is a projection matrix. And so let's think about what this matrix looks like. So there's 1 over the length of A squared. So that's a scalar. Now A is a column vector, and A transpose is a row vector. So we have a column vector times a row vector. So that's a matrix. It's an n by n matrix whose ijth component is ai aj. So it is a column vector times row vector. So this is not the inner product, this is the so-called outer product. And this matrix here is called rank 1 matrix. So the n by n matrix A transpose is a matrix of rank 1. Why is it rank 1? Remember what rank means. Rank means what is the dimension of the range of that matrix. Every vector which is in the range of this matrix P is parallel to A. So the dimension of the range has to be 1. And so therefore this is a matrix of rank 1. And so that's why we call it a rank 1 matrix. And so all columns of this matrix are multiples of the same vector A. So that's the idea. So projection operator is obtained from a vector A by taking A transpose and divided by the length of A squared. Okay, so we know how to project vectors on a given direction A, and you will get more let's say hands-on feeling of this soon when we start treating the data with projections. So projections are important. So you can always think that projection is kind of taking a shadow image of a vector. So you are projecting to a lower dimensional space. In this case, a one-dimensional space. You're just taking the shadow image, the orthogonal shadow image to that direction. I notice it's 10 o'clock. I'm not sure if I'm supposed to have a small break at some point, but so let me go a little bit ahead, and when I'm in a good position, then if you want, I can make a small break so that it doesn't become too heavy. Is that okay? Okay, so
Yes.
Okay. Yes.
okay, perfect. So I'll go a little bit ahead, and then let me see how many slides do we have. 1, 2. Okay, so I'm going a couple of slides ahead, and then we can make a. Okay, so we were looking at the projection to one single vector, but so often you don't have that luxury that you have one-dimensional space that you're projecting on, and so suppose you have a collection of orthogonal vectors, orthonormal vectors Q1 to Qk, and so then we look at the subspace spanned by those vectors from Q1 to Qk. Now, when we are talking about the projections, I'm arranging these vectors Q as columns of a matrix Qk. So this is a matrix n by k. So now the orthogonal vectors are columns of this Qk. And so if I have a vector v, which is in the span of those orthogonal vectors, so then by definition, this v is a linear combination of the columns. That's the very definition. And so then we saw that if you take a matrix vector product, the outcome is a linear combination of the columns. So therefore, I know that every vector which is in the span of Q1 to Qk is a product of Qk times a vector z, where z is some vector with k components. Z is in Rk. And so in order to find this z so that we have a projection, so let's see, I take an arbitrary vector x, and then I write that this vector is a vector in this subspace V. There should be a z here, so this is a typo, so it's not x, so this should be, well, no, yeah, it's okay actually, so sorry, there's no typo here. So decomposing my x in two pieces. I want to write it as a projection of x to the direction, to the space spanned by the vectors q1 to qk, plus a perpendicular part. And now this projection here is a member of this subspace V. So it is a linear combination of the columns of my q vector, so it can be written as qk times z, where z is I don't know yet. And then I have this orthogonal part, x perp. So this is the decomposition that I'm looking for. So I'm trying to find the projection operator PV here. And I know that this PV is of the form qk times z, where z is an unknown vector so far for me. And in order to find this z, I'm using again the fact that this x perp should be perpendicular to every component, every column of this matrix qk. So what I'm doing, I'm taking an inner product of any one of those q's. So I'm taking ql, and I'm taking the inner product of ql transpose x. And so then I'm plugging in this decomposition in terms of this unknown z. So what I get is this sum where I have these z's, and then I have the inner product of ql and x perpendicular. Now, if I have the projection built correctly, the second term should be 0. So x perp should be perpendicular to ql. So the second term vanishes. In this sum here, I'm using the fact that my q's are orthonormal. So ql transpose times qj is 0 if l and j are different, and it's 1 if l and j are equal. So this inner product here is picking only the term where j equals l. And when j is equal to l, this norm of ql is 1 because I had an orthonormal set of vectors. So what I'm left with is zl. Okay, so perfect. This is the way to solve for zl. And so therefore now I know what the projection of x to the direction of these vectors q is. So I'm writing now the projection of x using this expression here. So I have here this one. So I have zj's times qj's. I know what zj is. It is qj transpose x. So I'm plugging it in here. And so what I find is that the projection matrix can be written simply by taking the matrix qk times its transpose. So this is an n by k matrix, this qk, and this is an k by n matrix. And so I get an n by n matrix. So it is a square matrix, and its rank is k because every vector here is a linear combination of these qj's, where j is running from 1 to k. So the dimensionality of the image is always k. And so therefore I know that this PV is a rank k matrix, and this is how you form it by using the matrix qk. And the last thing that I'm saying here before we make a small break is let's look at the more general case where you have a set of k independent, linearly independent vectors a1 to ak. So if they are linearly independent, they are spanning a k-dimensional subspace, which I call V here again. Now I'm asking, what is the projection of x to this subspace? And I'm using the same logic as again. So I'm writing that x is the projection plus an orthogonal part. So x minus the projection should be orthogonal to each one of those spanning vectors because they are all members of this vector space V. So in this way, I see that x minus pvx is orthogonal to the whole subspace because it's orthogonal to any linear combination of those a's, and that the linear combinations are exactly the subspace V. So I'm writing this orthogonality condition here component by component, saying first of all that PV of x, which is in the vector space, which is the span of those basis vectors, it is a linear combination by definition of these AJ vectors. And so if I collect my AJs as columns of a matrix A, then this linear combination of the columns is simply A times Z. So you take the matrix A times a vector Z where the coefficients are collected. Now, x minus b vx is x minus ax. Okay, so we don't know what these Z's are, but we'll find out. And so then we write that these vectors here, this vector here should be orthogonal to every spanning vector aj. So that means that if I take any one of those spanning vectors aj and I calculate the inner product should give me 0. Now, if you think what this condition means, if I take the matrix A, where you have columns of aj, and you take the transpose, so then in A transpose, the aj transposes are the rows of A, and so therefore this set of conditions that I have written here, where j runs from 1 to k, can be written in a matrix form simply that by saying that A transpose times x minus az equals 0. So this is the orthogonality condition. And so these equations lead to what are known the normal equations. And now you see why they are called normal equations, because we are requiring that x minus az is orthonormal to, well, it's orthogonal to at. So let's see. This is the equation that I need to solve. So I know what x is, because x is an arbitrary vector. I want to find these z's. So what I get is that z has to be A transpose A inverse of A transpose x. So how do I know that this A transpose A is an invertible matrix? Well, it is a k by k matrix, and it is invertible because I assume that the columns of A are independent. So the fact that the columns of A are independent by construction guarantees that A transpose A is going to be an invertible matrix. And I can find those Z's by this formula. Z is a vector A transpose A inverse times A transpose X. And my projection then is, the projection operator of X is, let's go back, this is Z. P is A times Z. Okay, so I know what Z is here. So I multiply by A, and I get this formula. The projection operator acting on vector X is simply A times A transpose A inverse times A transpose. And this is an orthonormal projection to the range of A. So this is an important formula that we often encounter, so that you need to you take the independent vectors, you arrange them to a matrix A, and then you form A transpose A, and calculating this matrix gives you the orthogonal projection to the span of the columns of A. And I believe this could be a good place to have a small break. So how much break are we going to have? Maybe 10 minutes? Is that reasonable, or 15? What do you think?
It's the same, 10 or 15. It's the same. I don't know.
Yeah. Okay. So let's see. It's this. Yeah. So if we make a break of, let's say, we get back to I'm trying to make the conversion now. Here it's 10:12 now. So you have, let's say, 6 hours. It's 4:12 in there. So 4:25. So let's continue at 4:25.
Perfect.
Okay.
Okay. Perfect. Okay. Thanks. Okay, so let's get going again so that we get somewhere with this introductory part. So what I'm planning to do now is I'm going one more topic today on linear algebraic background, which is singular value decomposition, and then I'm starting to talk about principal component analysis, which is based on the singular value decomposition, so that it's not only linear algebra today, but you start seeing a little bit of data science also today. Okay, so without wasting time, let's move on. So now we have the concepts pretty much in place, and so now we look at the singular value decomposition. So before that, I have to define what is an orthogonal matrix. So if you have a set of orthonormal vectors, u1, u2, etc., un, so these are orthonormal vectors in Rn, and I collect them in columns of a vector u, a matrix u. So then I have what is known as an orthogonal matrix. And orthogonal matrices are characterized by the very nice property that the transpose of the matrix is the inverse of the matrix. So here is why. So I take u, which is written here, so u1, u2, etc., un. I take the transpose of u, and that means that I'm making the columns of u to be the rows of u. So the rows are u1 transpose, u2 transpose, etc., un transpose. And so then I'm calculating the matrix product. And the product is calculated simply by taking a row from u transpose and a column of u, and then multiplying them as inner products. And so I get a matrix whose entries are inner products between the columns of u. Now, if my u vectors are mutually orthogonal, so then all but the diagonal entries are 0. And on the diagonal, I have always the inner product of the vector with itself. Now, if these vectors are normalized so that their norm, that is the inner product, is equal to 1, so then I have simply 1s on the diagonal. So it means that u transpose u is the identity matrix of size n by n. Or in other words, I can tell that the inverse matrix of u is u transpose, because the inverse matrix is characterized by the property that if you multiply the matrix by the inverse, you get the identity. So the inverse of u has to be u transpose. And that's the characterizing property of an orthogonal matrix. And orthogonal matrices are convenient not only because the inverse of u transpose, as I mentioned, but also they are retaining the length of a vector. So if I take a vector ux and I multiply by u, and then I calculate the length of that matrix, then by definition this norm squared, which is the Euclidean norm, is ux transpose ux. Then I use the basic property that the transpose of a product is a product of the transposes, but in the reverse order. So I get x transpose u x. Now u transpose u was identity, so what I get is x transpose x, which is the length of x, or the norm of x squared. Not only, but also the transpose retains the inner products of two vectors. So if I have x and y and I calculate the inner product of x transpose u, then the inner product of ux and uy is the same. So the inner product doesn't change if I multiply both vectors by the orthogonal matrix. And basically that is another way of saying that the orthogonal transformation is an isometry. So it is a matrix whose first of all, the norm of the matrix is 1. Remember what the induced norm of a matrix meant. It meant that you are measuring how much the matrix is capable of stretching vectors. Well, an orthogonal matrix is not stretching nor shrinking. So you see here that it is keeping the length of the vector. So therefore, the norm of this vector must be 1. And in fact, you can characterize these orthogonal matrices. They are representing the following operations. They are rotations in space. You know, if you are rotating the space, you are not changing the length of the matrices at all. Reflection. So take a hyperplane and then reflect the whole space with respect to that. So you're looking in the mirror, basically. And the length of the vector and its mirror image is of course the same. Permutations. So you change simply the ordering of the indices in your vector, and that's an orthogonal matrix. So orthogonal matrices, they turn out to be either rotations, reflections, or permutations, are combinations of those. So when we are talking about orthogonal matrices, I like to think of rotation. That's my sort of the visualization of an orthogonal matrix. But of course you can have reflections and permutations. So they are very, very nice matrices. Now, turns out that all matrices, no matter what matrix you're looking at, can be always decomposed as a product of orthogonal matrices and so-called diagonal matrices. And so before I do that, before I state that result, I'm recalling you what a diagonal matrix looks like. So diagonal matrix is a matrix whose entries are 0 except for the entries in the diagonal. Now, if you have a square matrix, it's clear what we mean by the diagonal. If you have a non-square matrix, which is a rectangular matrix, so there are more rows than columns as in the first case. So then diagonal matrix means that you have a matrix which is non-zeros in the diagonal as long as the diagonal can go, and then you fill the rest of the matrix by zeros. So that's how a diagonal matrix looks like when n is larger or equal to p, so the number of rows is larger or equal to the number of columns. In the opposite case, when n is less than p, so that you have less rows than columns, so you do the same thing, you start filling the matrix along the diagonal and you fill as long as you can go, and then the rest of the matrix is 0. So that's how diagonal matrix look like in the case n is less or equal to p. So non-zero entries only on the diagonal, the rest of the matrix is 0. That's the definition of diagonal matrix. And so now here is the very fundamental result from linear algebra, saying that every matrix A, which is a real matrix of size n by p, can be expressed as a product of U, D, V transpose, where U is an n by n orthogonal matrix, so remember rotation basically. V is a p by p orthogonal matrix, again like a rotation, and then D is a diagonal matrix. Now, how many diagonal entries do you have in D which are non-zero possibly? Well, it has to be the minimum number of n and p, because if p is less than n, then you have p entries. If n is less than p, then you have n entries. So diagonal matrix has possible non-zero entries on the diagonal, and so you can only have the minimum number of the two indices n and p of those numbers. And these numbers are all non-negative. That's also important to notice. And they can be, of course, arranged into a decreasing order. And so sigma 1 is the largest so-called singular value. The second largest is the second singular value, etc. And this is the smallest singular value, the last one here. So the sigma j's are called the singular values of A. And then you have the matrices U and V. And the columns of U and V are referred to as left and right singular vectors of A. So what we are calling these vectors is not that important, but so the important thing is that you should notice that every matrix A can be decomposed in this way, U, D, V transpose. And that's called singular value decomposition of A. That's a fundamental tool in data analysis. And so one of the important things is to notice that if you apply A to Vk, where Vk is the kth column of your V matrix. So here we have the decomposition. So we have U and V, and I take the kth column of this V. And I'm applying my A to the kth column. Then I get the singular value, the kth singular value times UK. So this is an equation that is defining the so-called singular pair. So there is a Vk, UK is the singular pair, and sigma k is the singular value. This is a fundamental property. Now, if we remember what the norm, the induced norm of a vector is, a matrix is. So if we think what the maximum stretching power of my matrix A is in terms of the singular values, I realize that I cannot stretch any vector more than I can stretch V1, which is stretched by a factor sigma 1. So it turns out that this singular value, first singular value, sigma 1, is going to be equal to the induced norm of my matrix A. That gives me the maximum possible stretching that my matrix can do for any vector. Furthermore, if you have the singular value of A, then by taking the transpose of this singular value decomposition of A and remembering that transpose of a transpose is the matrix itself, so I get that A transpose is V transpose DT transpose U transpose. So I take transpose of all of the product and remember that transpose of the product is the product of the transposes, but in the reverse order. And so that tells me that if I have the singular value decomposition of A, I can automatically write the singular value decomposition of V, where the diagonal matrix is now played by, the role of diagonal matrix D is played by D transpose. Also, if you have a square matrix, and this matrix is invertible, then you can also write immediately the singular value decomposition of the inverse of the matrix. So here we assume that the inverse exists. And so in order to calculate the inverse of the diagonal matrix, which is now a square diagonal matrix, we see that the singular values all have to be non-zero. Otherwise, I cannot calculate 1 over a singular value. So this D inverse is a matrix whose diagonal entries are 1 over the singular values. This is not that important in this course. I'm just mentioning it here. And couple of comments still. So when we are calculating the singular values, there is no guarantee that the singular values are not zero. So it may well be, and it often is, that after some number of non-zero singular values, you start to get zero. So remember, the singular values are ordered in a decreasing order. So I take sigma 1, which is the largest, second largest, etc. I go to sigma r, and this is the last non-zero singular value. And after the sigma r, I just get zeros. So this is completely possible. So if this is the case, then it can be shown that the number of non-zero singular values is exactly equal to the rank of A. So the number of linearly independent columns of A turns out to be equal to the number of non-zero singular values. So if you have the singular value decomposition, it gives you a lot of information of the matrix. Just looking at the singular values, you can immediately decide what the rank of the matrix is. Just count how many non-zeros you have. And the rank, of course, is less or equal to the minimum of n and p. So because we only have that many singular values, so this is an obvious statement here. And so often, if you have zero singular values, you may want to discard all the the singular vectors which are corresponding to zero singular values. And it turns out that you can write what is known as the thin singular value decomposition, which is as follows. Take the singular value decomposition of your matrix A. So you have all the zero singular values there. Then throw away the zero singular values and keep only the non-zero singular values. And then form a matrix dr, which is a diagonal matrix of size r by r, where you have on the diagonal the non-zero singular values. So this is the first thing. Then take your matrix U and throw away all the columns that correspond to zero singular values. Take your matrix V and throw away all the columns that correspond to zero singular values. And if you do that, you can write your A as a product of UR, DR, VR transpose. So notice here we are using as economic expression of A in terms of its singular vectors and singular values as possible. So we are only keeping the non-zero singular values. So this is called a thin SVD. So it is thin in the sense that we are only keeping the pertinent information, which is singular values which are non-zero. So we just discard whatever is zero or corresponding to zero singular values. And when you have this thin SVD, singular value decomposition of your matrix A, you can immediately read what the read off from this singular value decomposition what the 4 fundamental subspaces for the matrix are. So the range of A is the span of the R left singular vectors, so the U vectors here. The null space is the orthogonal of the space spanned by the right singular vectors VR to V1 to VR. So it is the span of the here. So it is a span of VR plus 1 to V P, and so then the null space and range of a transpose, they are read off similarly by using the thin singular value decomposition of A. Again, what is important here is to notice that if you write the thin singular value decomposition of matrix A, what we need to remember is that the range of A is the span of the singular vector, so from U1 to UR. So this is the most important part, the range of A from our point of view in the applications. And here's another way of writing the thin singular value decomposition. So if you write in terms of the singular vectors, it turns out that you can write your matrix A as a linear combination of rank 1 matrices. So take the first singular vectors U1 and V1 and form a rank 1 matrix and multiply by sigma 1. Then take the second rank 1 matrix U2, V2 transpose, multiply by sigma 2, etc. And you go all the way to the last non-zero singular value, sigma R. And turns out that this is an exact decomposition of my matrix A. So there's nothing approximate here. This is an exact decomposition of my matrix A in terms of rank 1 matrices. And so you see that these sigmas are decreasing. So sigma 1 is the largest, sigma 2 is the second largest, etc. Sigma R is the last one, which is non-zero. Now, suppose that this last signal value is really, really small. So then you know that the last term here is of less significance, right? And so if you drop out the last term, for instance, here, you probably are not doing a big change in your matrix A. So you get an approximation of A, which is pretty close to A still, because sigma R is small. And so in general, we can say that if we want to have a rank K approximation of A, what we can do is we just retain the first K terms in this sum and throw away the remaining part. And the remaining part, if the singular values are small, has a small contribution to A, so this approximation is probably very good. This is something that we are going to use all the time when we are dealing with data. So we are characterizing the data in terms of the singular values and singular value decompositions, and then we are sort of approximating the data with lower dimensional data, which is obtained by using the singular value decomposition. So this rank K approximation of matrix A is a really useful and important tool. This is also used in image compression. So if your A is an image, and then you do the singular value decomposition of your image, you can compress your image by retaining only a few of the singular values and singular vectors, and approximating your image by the most significant rank 1 matrices, which are given by the singular value decomposition. So image compression is effectively done by using singular value decomposition if you have the singular value decomposition at your disposal. And so this is basically all of the linear algebra background. So let me now try to get to the second set of slides. So my plan today is that I'm starting with principal component analysis, so that you see in the first stage not only the linear algebra background, but also something which is related to, let me see, data science. So here is mine. All right. Sorry about my. Okay, so now let's go back to sharing. So I hope you see my screen again.
Yes.
Good, thank you.
Yes.
Full screen mode. Okay, so here we go. Perfect. So today, as I said, I'm going to talk a little bit about singular value decompositions and so-called principal component analysis. And so, as I said, this linear algebra part is playing a central role in my lectures, but I'm not using everything all the time. So I'm trying to remind you of the pieces of the linear algebra part when we go there. And so in this first section, first part, principal component analysis, the singular value decomposition is the most important tool. Okay, so here is a question. Suppose you are given a set of data. So x1, x2, etc., xp, they are data vectors. So they could be like let me see. They could be some patient data, for instance. They could be some sales data of people buying different things. They could be images. They could be whatever, but they are all assumed to be vectors of Rn. So whatever data I have arranged my data into column vectors, and I have p instances of this data. So my data set D consists of p data vectors, which are all vectors in Rn. So we have n attributes or n components in those. And so now I'm asking a couple of questions. So first of all, is there a way to visualize the data in a lower dimensional space so that we could detect if there are, let's say, clusters or lumps or structure in the data in general? So can we somehow look at the data in a visual way? And of course, if you have p-dimensional, n-dimensional data, it's really hard to imagine how the data looks like when n is large. So probably we'd like to have some sort of projection of the data to a lower dimensional space. And we should choose that lower dimensional space in such a way that is as informative as possible. So that's the idea. Also, if we want to do some sort of clustering or classification of the data, it may well be that our algorithm get too heavy if I use really high dimensional data. So sometimes I would just like to reduce the dimensionality of the data. So deal with the data which has less attributes than the original data, and then do what I want to do with that data. Whether it's neural network, whether it's whatever you want to do with the data, you may want to reduce the dimensionality. And so principal component analysis is basically the tool to do that. So here is an example. So this is an example where you have data which is redundant. And in this example, you know exactly in which way it is redundant. So suppose I have vectors xj, where j is running from 1 to p. So I have three-dimensional data. And the components of each vector is x1, x2, x3 here. But then, for some reason, I know that my data is given in such a way that the first component, x1, is equal to z1. And then there is another vector, z2. So that my second and third component are just different linear combinations of z1 and z2. So in this case, if I define a matrix A, which is given here 1, 0, the first row, 1, 1, the second row, 1, -1, the third row, and I take a 2 vector, which has components z1 and z2. If I multiply this 2 vector by this matrix A, I get my x vector. Well, if I have this structure, then why would I bother looking at my data X in 3-dimensional space, because I can represent my data in 2-dimensional space. So my data is in fact 2-dimensional, but it just looks 3-dimensional because 2-dimensional data has been multiplied by this vector A. Now, clearly, in this case, there is no problem doing this because I know what this matrix A is, and I can immediately calculate what these Z1 and Z2 are. But so if I'm given only these points xj, and nobody tells me that this xj data is obtained from a 2-dimensional data, is there a way for me to find this 2-dimensional representation of my data? So can I do this automatically just by looking at the data? So this is a data reduction problem. How do we get rid of the redundancy in our data if we have such redundancy? So you can think that let's say you have people who have bought a car and they have bought a car insurance, for instance, and then for some reason this car and the car insurance, they always come together. So you don't really need to know that the person has the car to know that the person has a car insurance. So so in that case, you might as well try to reduce the data. But of course, the data is not given you in that way. It is given so that the components they look like independent, but there is a dependency between the data. Statisticians would say that there's some sort of correlation between the data, and so we would like to find that correlation. So we are there. So there is a statistics language, and there is this linear algebra-based language which I'm following here. So in this example that I showed you, if I take two vectors u1 and u2, which I tailor by hand now, I'm defining my u1 to be 1, 0, 0, and I take my u2 to be 0, 1/2, -1/2. So because I know how my data was formed. So then if I take the inner product of this u1 and x, I get the z1 component, and u2 and x inner product gives me the second component. So here I have the reduction scheme. I take this u1 and u2, and then I'm just projecting my x in those directions, and I get the 2-dimensional data. But so suppose I'm just given the data. How can I find u1 and u2 if nobody tells me that there is this matrix A? Okay, so here is the so principal component analysis will give you that information. So this is a spoiler. I'm already telling you what the outcome is going to be. So but so see why. Let's see why this is the case. So first of all, I'm introducing a couple of concepts. So first of all, if I have this data x1, x2, xp, it's often nice to move the data around the origin. So what that means is that I'm subtracting the mean value from each one of those vectors. This is a process which is not necessary, but I'm doing it here for the sake of definiteness. So what I'm doing, I'm taking all the data vectors, xj. I'm taking the sum of them, and I'm dividing by the number of them. And so I get the mean vector. So this is the mean value of all my data. Okay, so average data. And so then I'm subtracting from each one of those data points the average x bar. So I get x1 minus x bar, x2 minus x bar, xp minus x bar. And so I'm denoting these columns that I get in this way by x1c, x2c, etc., xpc. C for centralized or centered. So I have centered my data. So effectively, geometrically speaking, you can think that you have a cloud of points in Rn, and you're just moving the coordinate system of your Rn so that it's in the center of mass of your data. Or another way of thinking is that you move your data cloud so that the center matches with the coordinate origin. And for later reference, I'm pointing out that if you have this matrix C and you want to pick the jth column of it, xcj, what you can do is you take the canonical jth unit vector. So ej is a vector with zeros all over except for 1 at the jth place. And so now if I'm multiplying xc by ej, I get the jth column. So this is a matrix, a linear algebraic way to express that I'm looking at the jth column of my matrix xj. Okay, so far we haven't done anything else but just moved around our data cloud so that it's centered at the origin. Now, suppose that I'm taking the thin singular value decomposition of my data. So you have the data, you center it, and then you go to your computer and you say, I want the singular value decomposition of my X. And in particular, I'm interested only of the thin part, so I'm only interested in the singular values which are non-zero. You don't have to calculate this necessarily. I will explain what you do in practice, because this may be a heavy calculation if the data is huge. Often we only need to calculate a few of those singular values and singular vectors. But for the sake of completeness, let's assume that I'm writing the centered data in terms of its thin singular value decomposition, which is this formula 2. And so the singular values are from sigma 1, sigma 2 to sigma r. So these are the non-zero singular values. And then the rest is going to be 0. So what is the jth component in my centered data? You remember that I told you in the previous slide that the jth component is obtained by multiplying by this centered matrix the jth canonical vector. So I'm taking this thin singular value decomposition here, xc, and I'm writing my xc in terms of that singular value decomposition. And so now I see that the jth data vector, centered data vector, is ur times something. And so let's see what that something is. I'm denoting it by zj. So you take ej, first of all, you multiply it by the matrix vr transpose, so you get a vector of length r. So there are r components in that. And then you're multiplying these vectors by the diagonal matrix dr. And so remember, there are only r non-zero components there in the diagonal. So what is this cj here? It is a vector, which you can read off from the previous line, dr times vr transpose times ej. And what this vector looks like is sigma 1, the first singular value, times the jth component of the first right singular vector, etc. Sigma r times the jth component of the rth singular vector. So there is a vector cj with r components, and what these components are is not that important. This is not necessarily how we calculate it, but what is important is that if you look at this formula that I've written here, this formula says that the jth column of my centered data, so the jth data point, is a linear combination of the columns of ur. So what I'm doing here is I'm presenting my centered data as a linear combination of the singular vectors of my matrix xc. And each one of those data points, xj, has this structure. So they are all linear combinations of the singular vectors ur. So here it's written in the more sort of compelling way. So we have the centered data cj, and it is a linear combination of u1, u2, etc., ur. And then there are some coefficients, c1j, c2j, etc., crj. And each one of these data vectors is represented in this way. So what we are going to call these u's here, we are calling them feature vectors. So these feature vectors are sort of representing all the data, because all data can be expressed as linear combination of these feature vectors. And the coefficients here are called the principal components of the data vector xj. So today I'm stopping here. I'm continuing on Thursday from here. So this is the last slide I'm showing today. But so the take-home message here is that when you have the singular value decomposition of your data matrix, all the data can be represented as linear combination of so-called feature vectors. And those feature vectors can be obtained by using the singular value decomposition and the coefficients are called the principal components of x, cj. And so I'm stopping here. So thanks everybody for joining today. And so we'll see on Tuesday, the same time, which is I think 3 o'clock in Naples. So
Yes,
so then,
yes, it's 3 p.m.
Yeah. So thank you everybody, and I will stop today here.